Good morning, everyone. Can someone chat and let me know whether you hear my voice?
We can hear you.
Oh, good. That's even better. You spoke too, so I'd know. Now I know both. I can hear y'all's and you can hear mine. So good deal. Hopefully everybody had a good weekend. I did not succeed in my task of making those practice tests. That will be finished hopefully today. I'll send an email out when it's done. I apologize. My boss gave me some other stuff I had to do, and I'm not blaming it on him because it was something that I should have done some time ago, like literally years ago. But now I have to do that, so still not finished with it. But I'm good enough spot where I want to stop that and get back to my classwork. So today, sometime the practice test will be up for the last test and for the final exam. Anybody have any questions before we get started? Any questions on anything? We are finished with chapter 43, for instance. We're going now into chapter 44. I'm not going to cover it exactly the same way your book does, but all the information that I cover will be in the chapter, and all the chapter information will be in what I cover. So that's the main thing. No questions? All right. Well, chapter 44 is called Astrophysics and Cosmology. And it's basically astrophysics is the study of the stars, employing the physics that we know about to better understand it and to make sense of it. And cosmology is a type of astrophysics in that we're studying the large scale structure of the universe, meaning stuff like well, we're on a size scale where we pretend individual galaxies, which by the way are hundreds of thousands of light years across. That's how big their diameter is. But in cosmology, you study the universe as if that is an infinitesimally small point. So you're really envisioning a huge chunk of space and seeing things that are really huge or just point particles. And then you try to make sense of the structure of the universe that we see, because we see that there are in fact clusters of galaxies, and then superclusters, which are clusters of clusters, and they're individual lone galaxies, but most of them are in groups. And like I said, the groups come together to form clusters, and the clusters can come together to form superclusters. And then you get these little tendrils and all sorts of crazy structure in space, which basically the largest things we see are walls and voids and stuff like that. So there's these tendrils, if you will, that are just strings and strings of clusters of galaxies that make what we call a supercluster, or an arm of a supercluster or something like that. And then they all go off into other ones, but there's huge areas in space where there's like appears to be no galaxies whatsoever, and those spots are really huge. And then there's of course areas where galaxies are all in three-dimensional, but basically three-dimensional, but only on a plane. So they're like two-dimensional, and they form walls that can be around those voids and stuff like that. But again, that's the huge structure. You can imagine if galaxies are treated as point particles, and then you're talking about the walls that form a void of billions and billions and billions of particles, or galaxies perhaps, then that's a pretty big size. So that's majorly what cosmology is about. And you sort of go back and forth between what's the area of cosmology and astrophysics, and it's not so important that you understand so much the difference, but cosmology is supposed to be sort of the study of the universe on a very large scale, and the astrophysics can be any part of that, including the cosmology. So it's kind of weird, but the ancient Greeks knew a lot more than people think. When you think of ancient Greece and Egypt before it and Rome after it, you think somewhat uncivilized humanity that doesn't know much. And in some sense, they didn't know a lot, but they were not, different as a species. They had every bit of the ability that we did intellectually. They just didn't have a lot of the technology. So they were able to come up with really, really big ideas. A lot of our data that we have to this day and can still use, for instance, the data that tells us that what we used to call Cancer might now be in location of what we now call Gemini, or vice versa. Weird little stuff like that. Basically, because the Earth's axis is sitting tilted like this, but it also does this wobble about once every, I think it's 27,000 years, somewhere around there. It's on the order of tens of thousands of years, and I usually look it up from astronomy classes, but that's not relevant to you. But because of that, the constellation that are winter solstice, and the constellation that are summer solstice, and the constellation that are vernal and spring equinox fell in, are actually changed now. So it doesn't make sense to say, Tropic of Cancer and Tropic of Capricorn, because those things have actually moved. But still, we only know that because the data from 2,500 years ago still exists, and we can, and it's good enough that we can measure it. So that gives you an idea how good the ancient Egyptians as well as the ancient Greeks were. They literally got data good enough for us to be able to not only detect that the constellations are moving and the stars are moving and the constellations are actually changing shape, but we can do so well that we can predict well into the future because we have really good data. And that's again because of not only ancient Greeks, but like I said, the Egyptians had a lot of data before that as well, and there's other civilizations as well. Some of them are later though, so there was a lot going on in South America, but that was kind of weird because that was long after what was already done in the northern Africa region of Egypt. So what we're going to talk about is that stuff, as well as modern cosmology and modern physics, our astrophysics, so that we can understand sort of the big picture of the universe right now. So I'll start off from sort of the ideas and thoughts of the ancient Greeks, who, by the way, again, were using the evidence and the data, partly that the ancient Egyptians would give us. And it's kind of weird, but this time period, for instance, if you take the time period when we believe Jesus walked the earth, that time period is not like we didn't have Egypt and Greece anymore. We just had, Rome, because Rome was in charge at that time. But no, those civilizations went on to exist. So you had in this Levant area of the Eastern Mediterranean, had an influx of people from cultures as diverse as ancient Egypt, as well as from Greece, as well as from other surrounding cultures like the Gauls and stuff of that from the northern parts of Europe. All those are all in the same little area. You can imagine how crazy and diverse it was. But that is the time where everybody's sort of learning stuff from other cultures and being able to take that information and run with it. And then the Romans, when they conquer and destroy the Greeks, basically, then they become an empire, and then they assimilate a lot of the stuff that they had. And in fact, that's why they were sort of more in power when we got the written word of what the planets were. And that's why we have Roman gods instead of the Greek gods for the names of our planets. For instance, Jupiter is a Roman god. Venus is a Roman god, and stuff like that. Mars, for instance, is another Roman god. And it has a counterpart in Greek culture, but with a different name. Actually, I've lost the name right now. I was just going to tell you the Mars one, but I forgot. Anyways, that's how all this came to be. So the ancient Egyptians had given us all this data. The ancient Greeks come along, take this data, and continue to build on it because they're intellectually curious people, as are to a slightly lesser extent the Romans. The Romans were more about I sort of compare them to more like engineers of the time. They're really good at monetizing and making better the things that other people created, but they weren't quite as interested in the actual research itself. And in fact, as they stopped being so interested in the research itself, and as Europe came online, it was actually what Thomas Jefferson would have called the Mohammedans, basically the people from the Muslim faith. They were the one that kept the knowledge going during the Renaissance and all that stuff, and or more specifically during the wars where we went out and tried to bring Christianity to the modern world. The research had more or less stopped in our civilization, our European. I'm not Native American, so I'm going to say our European culture. But during that time, it's not a redaction of history that I'm telling you. I want you to know this is actually true. I've heard people say on various networks and various things that this is, post 9/11 political correctness. No, it's not post 9/11 political correctness. It's the very reason why we have weird words like algebra and algorithm and sine and cosine and stuff like that, because the ancient Arabic population took over and built on the knowledge that the Greeks and to a lesser extent the Romans had, and they continued that research on. So they made big impacts, and they were, for instance, the world's leading cartographers when Columbus sailed and stuff like that. So that's kind of a neat little background. But let me tell you, so one of the first things the ancient Greeks did that was super helpful to science was they did this experiment, and I mentioned it to you before, about cutting something in half. So you take a chunk of metal and you cut it in half, and you take the half of that and you cut that in half, and you keep doing that over and over and over. And they knew there was two results that could happen. One, you could do it forever, or two, you couldn't. And they named that the atom because they thought the idea of being able to do it forever was just insane. So there's no way that could happen. So they assumed the second choice was right, which was that you get to some point where you couldn't split it no more. And as I told you, tom is something in Greek close to indivisible, or excuse me, divisible. And then a is like a prefix to say not. So atom, which we now call the atom, really means indivisible. And we know, of course, the atoms are no longer indivisible. It seems like the only things that we can't really break apart are now the leptons that I told you about, the gauge bosons, and the quarks. But still, we had that idea from the ancient Greeks. Well, the ancient Greeks also had another idea, and their idea was that either the universe is we're the center of it, or we're not the center of it. In other words, we might be orbiting around something that's the center of something else. And it's a common misconception, for instance, that people in ancient Greece are worse in Europe of the time of Christopher Columbus, for instance. It's a complete misnomer to suggest they didn't understand the Earth was round. That calculation was done by Eratosthenes and the Library of Alexandria well before Christopher Columbus sailed. And in fact, it's part of history that Christopher Columbus used the data that Aristotle had come up with, and such a trip might not have even been planned had he had the more correct value that Eratosthenes had done, because the diameter of the Earth, according to Aristotle, was way smaller than the diameter of Earth according to Eratosthenes. And like I said, Eratosthenes' data turned out to be much more correct. Because of that, that allowed him to think he had the technology to circumnavigate the globe. They did not have the technology. If there wasn't for a new world, they would not have ships big enough to keep them alive and sustain them for the trip around the whole Earth, if the whole Earth was nothing but water in Europe and maybe Africa and Australia. So they probably wouldn't even plan the trip. But luckily, one, they did plan the trip, and two, they were lucky enough to stumble across a whole other continent and various islands or whatever, because that was enough for them to be able to survive. So that's another happenstance of history. But yes, they very much knew the Earth was round. They weren't really sure about what the center of the universe was. And when I say universe in this ancient Greek and even ancient Egypt and ancient Rome era, we're talking about pretty much the sun, the planets that we know of that you can see with the naked eye, the moon, and the stars that we see. And that was the entire universe to them. Okay, and they thought it was, not much bigger than what we now know as our solar system. So they knew of Mercury, they knew of Venus, they knew of Venus, by the way. There's one. That's the ancient Roman god, the equivalent of Aphrodite from Greece. Okay, so Mercury, Venus, Earth, Mars, Jupiter, and Saturn were the only planets that they knew of. And in fact, that's where we get the names of the days of the week. You can trace them through their etymology, and you'll see that each day of the week, like Sunday's obviously the sun, and Saturday's obviously Saturn. It's a little bit more work to see how the moon, or excuse me, how Monday comes about, and how Wednesday comes out, and Tuesday comes out. And I drag that syllable a little bit for a reason. So anyways, that's actually why we have those 7 days of a week, is because there's the 7 heavenly bodies that they knew of. So we've got this idea that we're sort of the center of everything and we're not moving. And that's an idea of ancient Greece. They said, well, either we're moving or we're not moving. But if we're moving, then we should be able to see distant stars moving with respect to each other. So for instance, if we were actually orbiting something else like the sun, which we really are doing, right? Then when I'm over here, it's sort of like looking out my left eye and seeing I see a lantern, like a lantern you carry during a hurricane lamp or during a hurricane or something like that, or if you're just searching out at night back before flashlights were existed. Well, I see that right here, but when I look through this eye, I now see it over here. So it's wobbling back and forth versus the background just because I'm looking at it from this point and this point, and because there's a distance between these two eyes. So they said, well, if we were actually orbiting something or moving, we would see distant stars moving with respect to each other. Like the farthest stars away wouldn't move at all, but the nearest stars to us would show some motion. And they measured that and they found no motion of the stars. From that, they argued, well, either the universe is so big that we can't even imagine it, or we're just not moving. And it turns out they were actually just not quite imaginative enough, because the universe was that big. They didn't realize that the nearest star to us other than our sun was Proxima Centauri, which is like 4.2 light years away. You can see it from the equator, so that's one they could have seen. But even then, they didn't have the technology, because the distance between the two positions of Proxima Centauri from, let's say, from January to July, it's such a small angle they couldn't measure it. Okay, so they just didn't have enough imagination to imagine that the galaxy, the universe, or what they thought was the universe, was large enough to be immeasurable that way. Okay, so they started us on this idea of us being the center of everything. There were people at that time. I mentioned Eratosthenes, who was the one that basically determined the radius and diameter of the Earth, and obviously the circumference as well. But there's another guy who spelled slightly different, and I think his name was Aris, A-R-I-S, might have been A-R-E-S, Eratosthenes. He was one of the people that suggested, and God, I hope not, I didn't even look that up. I probably should have looked it up. We'll just say there's another Greek dude that suggested that the Earth orbited the sun. So that's in ancient Greece that they were making that argument. We don't know his motivations for it, because most of the documents that we have about him were destroyed basically during what, well, I'll call it the the medieval times, or the something along that sort, instead of calling it the Dark Ages, which my historian friends get angry when I call it the Dark Ages. But during the Dark Ages, a lot of stuff was burnt, and that's supposed to be medieval history. But again, when you see all these creations and stuff and inventions and discoveries, and then they stop for this long period of time, it's hard not to call that the Dark Ages. And then it picks back up afterwards for the Renaissance and the rebirth and all that good stuff. So anyways, the ancient Greeks did come up with that idea of us being the center, but the ancient Greeks also came up with the idea of us not being the center and us orbiting the sun. So we know that they came up with the idea of the molecule. The Eratosthenes actually was able to do quite a bit. For instance, he noticed, had talked to someone and learned that there was in fact a well. Now we're talking these like Mickey Mouse, or excuse me, not Mickey Mouse, I say these Bugs Bunny wells, like you used to see in Bugs Bunny cartoons, where there's like a little wall of rocks in a circle, and then there's a deep trench, and you got a little roof and a little pulley system with a bucket, and you throw the bucket down and then you crank it back up and that pour out the water, that kind of well. Okay, well, he heard from some travelers, Eratosthenes did, that there was a well in Syene that on a certain day of the year, the sun shined all the way down to the bottom of the well. That meant to him, since he knew the Earth was a circle or a sphere, that meant to him that the rays of the sun were shooting directly parallel to a radial line of the Earth. And he figured if he could find out how big of a shadow a pole at his location in Alexandria cast at that exact same time, he could use that to define or to find the circumference of the Earth. And then, of course, knowing geometry, the circumference is just given by 2 pi times the radius. So if he divided it by 2 pi, he'd get the actual radius. And if you divided it by just pi, he'd get the actual diameter. And lo and behold, he did that. And that's why he came up with the diameter and radius of the Earth. Sadly, like I said, though, his data was much better, or his calculation was much better than the one Aristotle did a long time later. But luckily for history reasons, we did send that expedition, or the Spaniards did send that expedition of Christopher Columbus, even though we know the Vikings have been there before. But he did send that specifically because he didn't think the Earth was that big. Now you can go on from that, and Eratosthenes and others also realized that, hey, when we see eclipses, that's something special. If you actually like had someone draw a picture of the eclipse, like let's say a lunar eclipse, if you draw a picture of a lunar eclipse at, let's say, 5-minute intervals for the whole period of the intervals, you could piece those photographs together, or those drawings together, and you would see that basically the shadow that the moon goes through is in fact a circular shadow, and it's therefore the shadow of the Earth on the moon. And from that, you can compare how big the moon is to the Earth's shadow. Well, that doesn't seem all that helpful, because we don't know how big the Earth's shadow is. We don't know how far away the moon is, and that sort of thing. But here's what you can do. Well, if you remember that a solar eclipse, when the moon blocks the sun from us, basically what happens is the whole disk of the sun, for people in totality of the eclipse, the whole disk of the sun is smaller than, or exactly the same size as, the disk of the moon appears. Angularly, they're the same size. Obviously, they're different distances away, so the sun's much bigger. But if you're in there, then what you know is that shadow cone comes all the way down to a very narrow, it's on the order of 1,000 miles wide, which is, or actually some on the order of a couple hundred, maybe like 600 or 700 miles wide. And that traces out a little swath across the Earth. And if you're in that little swath, then you get to see an eclipse, or a total eclipse. If you're outside of it, you're going to see a partial one. Well, what they argued is, okay, well, when the moon casts a shadow on the Earth, the shadow is reduced by 1 moon diameter, because it went from basically the size of the moon to essentially 0, because that width of that line is so small. So they said, okay, well, on the other side, the Earth should cast a shadow on the moon that's 1 moon smaller than the Earth really is. Well, from that, they were able to determine that the moon was about 1/4 the diameter of the sun. And when they had that, they then knew the relative sizes. Then they just needed to know how far away they were. That wasn't as easy as you might think, but they also realized that when you take a little piece of paper, say, and you make what's called a pinhole camera, so you can literally just poke a pinhole in a piece of cardboard, something preferably somewhat opaque. A thick piece of paper is nice, and the bigger the hole doesn't really matter. That actually sort of screws stuff up a little bit. So you make a pinhole, and then you hold it over the ground and move it up and down until you see a perfect little light image of the sun. I mean, you can literally, if it's big enough, you can see sunspots and all that sort of stuff. But there's only one distance away at which it comes into that good a focus. So if you take the distance away and compare that to the diameter, you realize that has to be actually a comparison of the distance away from the sun to its diameter. So from that, you can actually work out the diameter of, or the distance to the sun. And then, of course, once you have the distance to the sun, then you can work out the size of the sun. You can work out the size of the moon. And then if you get, for instance, a place where you realize that the Earth and the moon are supposed to be at 90-degree angles to each other, you can use some basic trigonometry or geometry and figure out how far the moon is. And that was all done by the ancient Greeks. So that really worked out, and they knew all that stuff, and they were fairly close. So they had good ideas of how far we were away from the sun. They had good ideas of how far the moon was away from us. They knew the size and diameter and circumference, radius, all that stuff about the Earth. They knew the size, radius, diameter, circumference of the moon. They knew how far the moon was away from us. They knew how far the sun was away from us, and that allowed them to create literal models. Sometimes they actually literally made physical models of the solar system. The Ptolemaic model was one of them, and that's spelled Ptolemy, Ptolemy. By the way, there's a buttload of Ptolemies in history because that became like an honored name, sort of like Caesar became an honored name after Julius Caesar. So you could be Caesar, but your name's not Julius or not Caesar. Same thing with Ptolemy. You could become a Ptolemy because of your family lineage and your royalty status in Egypt. So watch out. There's a bunch of Ptolemies, but the Ptolemy that created a model went off, and then Aristarchus comes along, and later on the Pythagoreans all get together and they work out a mess load of mathematics and build this model of the solar system, which has the Earth at the center, and then it has the moon orbiting it, and then outside of that are Mercury and Venus, and then outside of that is the sun. And this they worked with, and then beyond that, of course, you get Jupiter and Saturn as well. But that's the model. So let me show you what that model is and how that works a little bit so we can get some understanding of it. So their idea was that we'd have the Earth in the center like this. And then, of course, the moon is the closest thing to us. So that would be the moon, which I'll say big M. And then outside of that was Mercury. So I'll write that as ME. Now, here's the weird part with Mercury is we know that Mercury sort of did something weird. And in fact, all the planets did something weird. In general, when you look at stars from night to night to night, you'll see, for instance, a pattern that looks like this. And you'll repeatedly see that pattern, the same shape in the same section of the sky at the same time every year. So like maybe you'll see it in June and it'll always be there in June. It'll always look like this. But then every now and then you'd look up in this area and you'd see, oh, look, there's like something new here. It looks like a star that I've never seen before. And it'd be right there. And the next day, or the next week, I should say, it's usually on the order of several days before you can make sense that it's moving. It'll go through this sort of path. And it might even do something crazy like get brighter. Like this. So what we see is the thing appeared to have gone in a little circle like that. Okay. It was as if the object wandered through, and that constellation, by the way, is Gemini. Gemini. It was as if this object wandered through, and lo and behold, the Greek word for wanderer is planetos. So we had the stars that seemed to not move. I mean, they moved. You could see them moving, like they'd rise at a certain time of the day and they set at a certain time of the day. And you could come back months later and they might not even be up, but in a consistent way. Once we got off the lunar moon, once we got onto the non-lunar calendars, then we were able to see that the same constellations were up in the same month. So if you had Gemini available to be seen in July, then Gemini would always be visible in July. And if you didn't have it visible, say in May, then it's never going to be visible in May. And that was the case for all the constellations. But on top of that, you had these wanderers that would wander through some very specific constellations, and those constellations became the zodiacal constellations, the zodiac. Okay. And they are along what we now call the ecliptic. And they named it that. We call it that now too, of course, but they named it that specifically because they realized when the sun or the moon was on that, they would get an eclipse. And what it was to them is they thought it was the actual orbit of the sun around the Earth. But in fact, we now know it's sort of a picture of where our sun appears to be. So that's what the ecliptic is modern day. So they imagined, in fact, this model on the outermost part of which is a giant crystalline sphere. And all of these orbits, by the way, are crystalline spheres. But this one actually has to have a circle on a circle, and that would be Mercury. So this was called an epicycle, or this was called an epicycle, and this was called a deferent. And then we had another one out here, which was also on a circle, whose center lined up with this center. And that one was Venus. And then there was as if there was an imaginary line running right through these centers, and that was where the sun was. Okay, so in order to make sense of the data that they had, and they had hundreds of years of data when they're making this, they had to have the Earth at the center, but because Mercury never went very far from the sun, they had to account for that. And sometimes it went the same direction as the planet was rotating. Sometimes it went the opposite way. So putting it on this little thing made sense of this doing that, right? That loop. And it getting brighter over here just means that's when the planet is closest to you, because obviously if it's bright and it's closest to you, then it's going to be brighter when it's closest to you. So that's why it got bright over here in this part. Venus did the same thing, only it could get farther away, so they made a larger epicycle. And then the sun didn't do any of that crazy motion, so they didn't make anything out of that. But then outside of that, they had Saturn. And then outside of that, they had Jupiter. They actually ultimately put epicycles and deferents on all of these to make the data better, because they're getting better at taking data and measuring things. But every year they would notice it got a little off. So they would make a new, basically they made these books that they would sell, the astrologers would sell, and those books would be either sold to the government, or the government would commission them to make them. And they do all these calculations because you had ceremonies and everything basically based on the pseudoscience of astrology. So they made decisions based on where the king's birth constellation was, what was in it. Was Mars in his birth constellation? If Mars is in his birth constellation, that could mean war. Of course, you couldn't really get astrologers to all agree on what all the things meant, so that's why we put the word pseudoscience in front of it. But that was the whole picture here, and these astronomers would make this up, and every 5 to 10 years they would have to make up a new one, and they would take everything they've seen since then and make corrections. So they'd tweak the rate at which this goes around there, they'd tweak the rate at which maybe not the rate at which this center goes around, but the rate at which the planets go around, or they tweak the rate at which this would rotate around there, and again tweaking the radius and all that stuff. And they do all that, and of course then beyond it they thought was the crystalline sphere that they sort of, in some groups they pictured this crystalline sphere as opaque, but it had little holes in it, and the holes in it were the actual stars. So there was fire outside of this, fire outside of the crystalline sphere, and that giant fire was the twinkling that you saw through the little holes in the crystalline sphere that might make up, a star named Deneb or something. So that was the Ptolemaic model. And it did really well, like literally, as long as you every 5 to 10 years or so got back and redid the data and tweaked it a little bit, you could predict where all these things would be for the next 5 to 10 years. And that's what, for instance, Galileo did. That's what Kepler did. Aristotle had done it, of course, because this originally started off as a Ptolemaic model, but Aristotle took it and run with it, as did the Pythagoreans and various other groups. So that was the model of our solar system. And then, like I said, all the stars were holes in a sphere. Some really far distance away. I might be drawing a little too small, but not as far as the nearest star is to us, really. So that was their whole model of the universe. And that you can see, once this was interpreted from Aristotle's word, basically science stopped for about 2,000 years in the European world. Okay, as I said, things continued in the Arabic world, but on the order of 2,000 years, sort of science stopped. And the Dark Ages obviously wasn't 2,000 years, but I'm saying a lot of stuff stopped because people were relying on the word of Aristotle. And part of that was because by this time, we had a Christian church that was sort of in charge of everything, and they had already interpreted all the scriptures in terms of this, and it made perfect sense that the earth was at the center. Aristotle's laws of motion were that there's two types of motion. There's natural motion and violent motion, and natural motion is just the 4 or 5 elements going to where they're supposed to be. So the elements under Aristotle, of course, the elements were earth, air, water, and fire. Of course, there was also a quintessence, which is Mila Jovovich. And that was meant the heavens. Okay. So if you ever saw the movie Fifth Element, congratulations, you're one of the 8 people that got that joke. So, so this earth, air, water, fire thing was basically used to explain everything. So natural motion is when earth is trying to get to the center of the earth. So when you burn a log, which is mostly earth, but it's got some air in it and some water in it as well, when you burn it, the smoke comes up, and then part of it falls back down as ash because that's the earth part trying to naturally get to the center of the earth, which is its natural place. Part of the smoke lifts up, which is the air, because the air is supposed to be lifting up above the earth's surface. And part of it's actually fire, and fire is like the sun. It's supposed to be up near the sun. So that would explain why the various velocities were what they were when you watch some dust and stuff coming, or ash and stuff coming off of a fire. He pictured certain first principles that were things he assumed were true, and that you couldn't prove them, but they were just so naturally obvious that you didn't have to. Like the heavens are perfect. The perfect shape is a sphere. The perfect shape in 2 dimensions is a circle. So in the heavens, since they're perfect, everything must be a circle or a sphere. You can see that's kind of weird and not really what we think of in everyday life, but that was his principles. So that's why we got all these circles, and they had to be circles, and that's why the earth had to be the center. And all the scripture was built and interpreted based on that. So they had a vested interest because the church at one point was ruling the world, the Catholic Church, and then of course we got the Protestants and all that. But for a long period of time, we had a Catholic Church that was sort of running everything, and they wouldn't allow too much, but they still needed the astronomers to make the annals that they could use to predict dates and stuff like that. Like even Easter. Easter's supposed to be, if I remember correctly, it's related to the first full moon after the summer solstice. No, after this vernal equinox. Yeah, after the autumnal equinox. So it's like the first full moon after the vernal equinox or autumnal equinox, and then the first Sunday thereafter. That's basically the way they find it. So you got to know the motions of the moon and the motions of the earth, quote unquote, actually what they thought was the motion of the sun, so that you can predict those dates just to celebrate certain things. So that was their grandiose idea, and it turns out it's not that bad. To this day, this is what we teach in our astronomy class. The first thing the students need to learn is something called the celestial sphere. So you can imagine the Earth as if it's this little itty bitty sphere here. Okay, and let's imagine, for instance, we're on top of the Earth. So this is us in Virginia. That would mean the equator is about like that, and that would mean the axis of rotation is about like that. Now, if you imagine a sphere that is way, way bigger than this one is, but it's still a sphere and it has the same center, then this is just like the celestial sphere or the crystalline sphere that they had in the Ptolemaic model. And if you trace this line out to here, you get the north celestial pole. This word is celestial, which means star-like. And down here would be the south celestial pole. And then lo and behold, right on top of this is the celestial equator, just like this was the equator. Okay. And then you can make a coordinate system like our longitude and latitude system. And that coordinate system will help you figure out all the points in space. But in 2 dimensions, just like we only need longitude and latitude to find the points on the surface of the Earth, but we need an altitude if we want to find the height. Well, in this case, this is all picturing the outer space as if it's a 2-dimensional spherical surface. So it has a positive declination from 0 to 90, and it has a negative declination. So if you go down 10 degrees, this would be negative 10 declination, and anything on that particular line, which is really a circle, would have a declination of negative 10 degrees. And then there'd be another one and another one. And like I said, it goes up to 90, which would be right here. And then you have a similar one like this. So these are like the lines of latitude on the Earth, but they're on the celestial sphere. Now, what we also know is that the sun appears to do this crazy thing. It traces out an ecliptic, and that ecliptic does basically this. It crosses the celestial equator, comes down here, reaches its highest point due south, and then comes back here, crosses the celestial equator again, so on and so forth. And again, making that into a 3-dimensional shape as opposed to the flat when I started drawing, you can get certain dates that are important, like when it crosses the celestial sphere or the celestial equator. That's actually, and that actually should be here. That's an equinox. And this highest and lowest points are solstices. And solstice means the sun stood still. So the solstices are the longest day. If it's above the equator like this one would be summer solstice because we're biased for the northern hemisphere, not for the southern hemisphere. And this one would be the winter solstice. So that's our shortest day of the year in the northern latitudes. And it's the longest day for Australia, for instance, and New Zealand. So all this comes together, and you can actually use this model because you realize, okay, in reality, what's going on is the Earth is rotating this way. Well, you just picture the celestial sphere rotating this way, and you can predict that stars are going to move up and to the right if they're to the east of you. They're going to move down and to the right if they're west of you. They're going to move in a clockwise circle if they're south of you. They're going to move in a counterclockwise circle if they're north of you. All of that came from the ancient Greeks, and we still teach it to this day because it was so darn correct, right? It's completely wrong, but it was so fitting because over a human lifetime, these constellations don't change shape significantly. So that allows us to predict things and all sorts of cool stuff like that. And that is basically how the science of astronomy sort of grew out of the pseudoscience of astrology. And from that, they were making sense of the universe, and they were able to, for instance, figure out that there's seasons, there's times when things can grow. You don't have to be a hunter-gatherer anymore. Once you get to that point in civilization, you can have art, you can have music, because the people have a way of getting what they need, food and stuff of that sort, and clothing from other people. So not everybody has to hunt and gather. They can have people that hunt and gather. They come back and sell their stuff. They have people that are artists that can make art, and they sell that art and use that money to buy food and stuff like that. That's when civilization can become, quote unquote, modern, or a good modern civilization that has the freedom to do art and music and study, science and stuff like that. So all of this came to some extent to a head in the ancient Greek world. And then, like I said, the Romans took off with all the cool stuff they learned from the Greeks, and they made aqueducts, and they made, lead pipes and lead crystal wine bottles so that they could sweeten their wine also with lead. So they got all sorts of cool stuff made out of all this, but they were really very good at applying the knowledge that other people grew. And some people were, it wasn't like the whole Roman world was interested in something other than science. There were still Roman people and people in the Roman culture that were interested in science. Just most of it was now just being used in an engineering way as opposed to a discovery way. So then comes along a guy by the name of of Kepler, and Kepler. Well, actually, I'll first go with Copernicus. Then comes a guy by the name of Copernicus, who's actually a member of the church. He's pretty well respected within the church, but he's looking at this model, and there's even like a quote where I think he's wrote to Galileo or Kepler or somebody, I can't remember who, but it said, if I had been around, maybe that actually was a quote of Kepler. He said, if I had been around when God made the universe, I would have made it a little more simple. Right, because this is a really complex problem to solve. All these circles on circles. It's sort of the reference they made in A Bug's Life when they said tunnel within a tunnel, complaining about the one little ant that was interested in discovering things. So they were making a reference to this Ptolemaic model, but basically Copernicus said, hey, we've lost our way. We've lost our way from what Aristotle taught us. We've got epicycles, difference, equipoints. They actually had points where the center of rotation for the different objects were off the center of the earth and weird stuff like that. And it made it very, very complicated. And he was disgusted by how far we had drifted away from what Aristotle taught. So he figured out a way that if you put the sun in the center, then the natural periods, the fact that Mercury, for instance, has a shorter period of rotation than Venus, if you put them around the sun like this, so this is Mercury, Venus, Earth, Mars, Jupiter, Saturn, all of them in perfect circles, then their periods make perfect sense. But he was in no way going to consider anything other than a circle, because he's really just trying to get back to Aristotle's teaching, which is why I separate the Copernican revolution from the scientific revolution, because Copernicus did the right thing for all the wrong reasons. He did it because of an appeal to authority, whereas the scientific revolution was, hey, we're going to, one, let science and experiment tell us what's right and what's wrong. We're not going to trust authority that way. And two, we're going to realize that, oh crap, we're just the third rock from a insignificant star in a pretty good size, a pretty mediocre solar system, but in a pretty good size galaxy. But also we're one of a billion species. And in all that sense, we're not the center of everything. We're not special necessarily. It's not like this universe was made for us. We're just a part of it. So that's the continuance of the scientific revolution, whereas the Copernican revolution was just getting a heliocentric model. So that's the heliocentric model. So he did that, and his data was actually pretty good. But in the meantime, when his data came online, we had a guy by the name of Brahe. This was Copernicus. We had a guy by the name of Tycho. I think it's Tycho, but I think it's pronounced Tycho Brahe. Now, he was from noble blood, and he was very good at convincing people to give him money, particularly royalty. So, for instance, the Danish government gave him, he's from Denmark, obviously. They gave him an island, and they paid for him to build they somewhat paid for him to build an observatory. And this was before the invention of the telescope. He just had an observatory, which was more or less a protractor built into a wall with a hole in the opposite wall, so that he could measure very precisely the positions of stars through that little hole. And he was brilliant, but he was also kind of an arrogant butthole. In fact, he lost his nose in a sword fight in college over who was the better mathematician. And he wore a silver and brass prosthetic nose that he held on with wax. But he was also he's sort of the Russell Brand of the ancient world, or of the, let's say, the Renaissance world. And along comes Kepler, gets a job with him, and he's sort of the Mike Pence of this world. Okay, so you can imagine Tycho Brahe's Russell Brand, Forgetting Sarah Marshall, and what were some other movies he played in? Get Him to the Greek, that guy that used to be married to what's the singer that Russell Brand used to be married to? What's her name? I can't remember anybody's name. Anyways, so
Katy Perry.
yeah, that's it. Thank you, Katy Perry. I just saw her last night. And I couldn't remember her name. So yeah, he was married to the Katy Perry, and he's got this idea of a drug head and a major stoner, sexaholic. If you read his bookie wookie, he was a sexaholic. So imagine that's Tycho Brahe, and now imagine our former vice president Mike Pence. Really straight laced, very conservative kind of guy. Well, that's what Kepler was like. Kepler also, poor guy, he's horribly sick. Like he's constantly got rickets and all sorts of crap. He's got to go back every couple of years to his home and get his mother out of jail for being accused of having being a witch, which was a common problem back then. Once you were a maiden that had no man, like you were widowed and your teeth fell out, you just look creepy to men. So we're just gonna put you in prison because we're pretty sure you're a witch. And he had to fight that. But anyways, he had written a letter about his idea of a model of the solar system that was Copernican in nature, but it actually used the fact that the number of planets happened to match the number of perfect solids. And he sent that to Brahe and various other people. Brahe's like, oh, this is the mathematician I need to work out my model, because Brahe had another model. It was sort of like this. It had all this except for the sun. So all of this was normal from the Ptolemaic model, but he had the sun over here and all that crap orbiting the sun. That was Brahe's model, but he couldn't get the math to work out. So he needed a brilliant mathematician. So he hires Kepler. And then poor Kepler sees this guy and he won't give him his data because Kepler's or Brahe's realized that Kepler's brilliant enough that he might outshine him. So he gives him a little bit of data at a time. And eventually what happens is Tycho Brahe, who's known to party, I mean, he had a pet human. He had it was basically a pet little person. So, what people used to refer to as midgets, or people that, had stunted growth. He had one of those as literally a pet. He once got a deer drunk in a party, and a deer fell down the steps and broke its neck and died. He had a monkey as a pet. He would basically party all day, and then at night, he'd get out and do his observations, and then he'd sleep, until 2 or 3 in the afternoon, and then start partying again. And because he was royalty, he wouldn't let anybody know that he actually peed and pooped. So one day he sat there for too long until his bladder exploded, and he died of sepsis, which is, by the way, the same death that George Washington had. But he died, and then Kepler couldn't get his data. Finally, Kepler got the data from the courts. They ordered it, and despite the differences they had, Kepler dedicated the whole thing to Tycho Brahe, because Tycho Brahe was so good, he could discern between this model and Kepler's model with his data. So Kepler tested his data and realized I had to throw away the Copernican revolution, the Copernican idea of circles, and he had to go to bastardized versions of circles, which Copernicus would have died over. So we're up to now the point where we have a heliocentric universe, and I will continue next time with a discussion on basically the rest of modern cosmology and astrophysics, and we'll get into light years and the Big Bang Theory and all that good stuff. So you guys are free to go. If you have any questions, just stick around. I'll wait for the last person to leave. Thanks for coming, everyone, and I'll email you when the practice tests are up.
Yeah, I was wondering if you had a plan for those. What is the current plan for the final again? Is that Monday,
So
Wednesday?
Your final's Wednesday.
Wednesday? Okay.
And the practice final will be up today. So that gives you still more than a week. So I don't feel too horrible about that. But I also am going to give you a test just on probably these last 3 or 4 chapters. That will alleviate me from having to do 43 and 44 on the actual final. So I'm going to have 2 practice tests, one for a new test on whatever we've done since the last test. And then, like I said, a practice final for preparing for the final exam, which is comprehensive.
Gotcha. All right. Thank you, sir.
No problem. See you, Gavin. Cadmium, Elizabeth, anybody else have any questions? Josh?
Are you finished with the labs now, or are you?
Yes, I decided we're not going to do any more labs. I'm going to do review sessions for all the lab times that are optional. You can come to them if you like if you have questions, I recommend you coming. If you just want to see what other students are having problems with, I recommend you coming. But I'm not checking roll or anything like that. I'm just doing this for you guys. And I'm letting all the ones come together.
I just had a quick question. So I heard you at the beginning of the class said that you've been quite busy. So I'm not like, I don't know. Yeah. But I just wanted to remind you for the last test that we have, I think chapter 11 and 36, those questions are still hidden from us.
That's the very next thing on my list. I still have that sitting here. It's the very next thing. I'm probably going to do that before I even make the practice test.
No problem. Thank you so much.
It'll be finished in probably within an hour.
Okay, awesome. Thank you so much.
No problem. Thanks for reminding me.
No problem.
Mary, Vincent, anybody? Bueller.
Yeah, I have a question. I'm just gonna stay till last.
Okay, go ahead. Up, so it's you and Vincent. Vincent, do you have anything? Are you here? Okay, I think he's out. So is it a private question? Would you like me to stop